Hello everyone, I welcome you all to the platform of Padre Chemistry. So students, we were discussing about the previous year questions of the chapter that was Kinetics. Two of the parts already we have discussed. Now this is gonna be the part number 3 in this. Okay, so let us begin with the solutions. So before starting the video, students, if you wanna prepare for CSIR NET, GATE, SET or the assistant professor exam, courses are available on the Padre Chemistry. These courses comes with three months, 6 months and with the 1 year validity, in which you will be getting the video lectures, test series, assignments and along with that the PYQ solutions you will be getting. For more details you can contact on these numbers which are being shown on your screen. Okay, so let us begin with the solutions to the next questions. So this question, it is from your CSI exam that was conducted in the year 2016. CSIR 2016, in the December month this question it was asked. So the question it says the rate of an acid catalyzed reaction in the aqueous solution, it follows the rate equation. This rate equation is given if K16 and K4 are the rate constants for the reactions at the ionic strength 16 moles per liter and 4 mole per liter respectively. What is this ratio? That is natural log of K4 to the K16, where K in terms of the Debye-Huckel constant, that is Bs. Okay, so this is from your salt effect. The salt effect. Now here instead of the two ionic species, three ionic species are being involved, which is X positive, Y2 negative and the H positive we are having. So whenever we have three ionic species are being involved, so in that case your log K value, it becomes equal to log of the K naught plus of the 2A. Instead of the A Debye-Huckel constant, here it is in terms of B, so that we can keep it 2b into the ZB plus of the ZB into the ZC plus of the ZC into the ZA into the root of ionic strength. So this expression you have to use when three ionic species are present. Okay, where ZA, ZB, ZC are the charges present on the ionic species. So first is if the ionic strength it is 16 moles per liter, at that point log K16 it will be log of the K naught plus of the 2b times the charges on the first ionic species, it is +1, on the second one it is minus of 2 plus of ZB, which is minus of 2 into the ZC, which is plus of the 1 plus of ZC into the ZA, which is +1 into the +1 into the root of ionic strength, which is 16. This is what we will be getting. This becomes equal to log of the K naught plus of the 2b times, this will be minus of 2 plus of the 1 into the root of 16, which is 4. So this comes out to be as log of the K naught plus of the 2b into the 3 minus of 3 into the 4. So 4 3s are 12, 12 2s are 24. So minus of 24b and the log K naught, this is equal to the log of K16. So this is what we will be getting. Now similarly you can find it for the log K4, that is when the ionic strength is 4 mole per liters. So log of the K4 is will be equal to log of the K naught plus of the 2b times that ZA ZB into the ZB ZC into the ZC ZA, that products, and on solving substituting and we have got it as minus of 3 into the root of ionic strength, which is the 4. It comes out to be as log of the K naught plus of the 2b into the minus of 3 into the 2. So it comes out to be as minus of the 12b. This is log of the K naught. This is equal to log of the K4. So this is gonna be the value, right? So now the ratio we need to find is for the K4 to the 16. So log of the K4, so subtract these two now. Log of the K4 minus of the log of K16, this will be equal to log of the K naught minus of the 12b and minus of the log of the K naught minus of the 24. 4p. So this log k0 and log k0 will get cancelled out. Answer we will be getting it as 12b, that is equal to log of the k4 upon the k16. So this is gonna be your answer, which means the option D, it becomes your correct answer for this one. Okay. So the next question now we have is this one. This is from your June exam conducted in the year 2017. It says if the pre-exponential factor in the Arrhenius equation is this much, which means the A's value it is given to us, value of the rate constant at extremely high temperature. So according to the Arrhenius, the rate constant K, it is equal to A into e raised to the power of minus of the EA upon the RT. At extremely high temperature it is given, which means that T is approaching to the infinity, which implies EA upon the RT will be approaching to the 0. So the rate constant K, this will be equal to A into e raised to the power of 0, which implies rate constant K, it is equal to the A only. So this value of the A, it is known to us, which is 1.6 into 10 to the power of 12 second inverse, and this is only gonna be the rate constant, which means the option A, it becomes the correct answer. Okay, next one is this question we are having. This is says in an enzyme catalyzed reaction, the values of the K2, and if the E0 value is given, the magnitude of the maximum velocity and the turnover number is being asked. So turnover number, this is nothing but your rate constant K2 a name is given to it. So now its value it's already given to us, which is 3.42 into 10 to the power of 4 second inverse. So this K2 value is this much. Now the other thing is maximum velocity, which means they are asking the value of R max. Right? Now R max is nothing. It is equal to the K2 times the E0 value. So K2 is given, which is 3.42 into 10 to the power of 4. E0 value is also given, 1 into 10 to the power of minus of 2. So this comes out to be as 3.42 into 10 to the power of 2. So this is R max and the K2 value or the turnover number value. So the answer, it becomes the option A. You see here it is 10 raised to the power of 2 for the R max and 10 raised to the power of 4 for the turnover number. Okay. Moving upon to the next one, this question you are having. So this question it says in the kinetic study for a chemical reaction, the slopes are drawn at different times in the plot of the concentration of the reactants versus the time. So the plot is for the concentration versus the time, like this the plot is drawn. Okay, the magnitude of the slope with the increase of time. So for any reaction, that is suppose A getting being converted into the product B, with the due course of time, this reactant's concentration it is gonna decrease. That means A's concentration it decreases with the due course of time, with the due course of time. And due to that, if you draw a plot for the concentration versus the time, the magnitude of the slope, which represents the change that is occurring, that too decreases with the due course of time. Reason is this one. Okay, so the answer will be the option C in this case. Okay, next one is this question we are having. So this says Arrhenius equations for two of the reactions with the rate constant K1 and K2 are given. If E1 is greater than that of A2, then at a given temperature, which of the conditions will be applicable? So K1, it is A1 times e raised to the power of minus of the E1 upon the RT and the rate constant K2, this is A2 upon e raised to the power of minus of E2 upon the RT. The ratios of these, if you take K1 upon the K2, this will be equal to A1 times e raised to the power of minus of E1 upon the RT, and this will be A2 into e raised to the power of e minus of e naught upon e2 upon the RT of it, right? So this we can write it as a1 upon the a2 into e raised to the power of e2 minus of the e1 upon the RT, right? So now it's given that my e1 it is greater than that of e2, which means this difference which is of the e2 minus e1 that we are having, e2 minus e1, this is gonna come out to be negative value, right? Because e1 is more as compared to e2, so this is negative 1. So which means in this expression, that is for the ratio k1 to the k2, this is equal to a1 upon the a2 into e raised to some negative power we are having it, which means this exponential power it is gonna be negative. So if I multiply a1 by the a2 ratio with some small value, so overall k1 by the k2 value that I'm gonna get, it is will be a smaller one as compared to the a1 by the a2, right? So which means that my a1 by the a2 value, it's gonna be greater as compared to the k1 by the k2, because after multiplying it with the smaller value only the k1 by the k2 ratio I'm getting it, which will be definitely a smaller value, right? So this condition will be applicable. So a1 by a2 is greater than that of the k1 by the k2. Option 1 it becomes the correct answer. Okay. Next is this question. A photochemical decomposition of the HI, it takes place with the following mechanism. Okay, considering the hydrogen and the iodine atoms as the intermediates, the rate of removal of the HI, which means minus of the d by dt of the HI, this is being asked to us. Okay, so include all the reactions where this HI substrate is being involved. So in the first reaction, which is HI plus the H nu, which is of the intensity IA, this is giving us the H plus of the I. If you write the rate expression for this, it's gonna be minus of d by dt of the HI, it will be equal to IA. I, that is the intensity A which is given to us. So this is gonna be the rate for this. The second equation, which is H plus the HI, this is with the rate constant K1 giving us the H2 plus the I over here. So for this one, minus of d by dt of the HI, this comes out to be as K1 times the H into the HI of it, right? So these two we can combine it. Overall, d by dt of HI we are getting it as IA plus of the K1 times the H into the HI of it, right? This is what we are getting. Now here this H species, you are seeing it is not present as the substrate, okay, because it is your intermediate. It has been used in, sorry, this H, this is formed in the this step and is being consumed in the second one. So this is your intermediate. So we need to apply the SSA over here so that we can eliminate this H term from the final expression, right? So for that, what we will be doing it, SSA on the hydrogen atom. So for this, d by dt of the H, this will be equal to the 0, right? So here in the first expression, that is HI plus of the I observed, this is giving you the H plus of the I. This is the expression. So for this one, here only we can write this, that d by dt of the H, this is equal to the I observed, right? And the second one where it is getting being consumed, it will be minus of d by dt of the H. This will be equal to K1 times the H into the HI. This thing we will be getting. So combine these two now. It becomes d by dt of the H. It will be equal to IA minus of the K1 times the H into the HI of it, right? This is equal to the 0. So from here, IA upon the K1 times the HI, this is the concentration of H that we will be getting it. Okay, so now this H value that we have got it, just substitute in this expression which is gonna represent the rate of removal of the HI. So minus of the d by dt of the HI, this becomes equal to the IA plus of the K1 times the HI into the H, which is equal to the IA upon the K1 into the HI. So this and this gets cancelled out. So it becomes equal to the IA plus of the IA, that is equal to 2 times the IA. So this is gonna be the rate of removal of this HI, which implies it is the option C which becomes the correct answer in this. Okay. Next is this one. So these were all the questions from your June 2017. Now we are beginning with the December 2017 exams. It says for a sequence of consecutive reactions A to the I and then I to the P with the rate constants K1 and K2, the concentration of I would be by a steady state approximation. Okay. So the reaction is A to the I, this is with the rate constant K1, and I to the P with the rate constant K2. So di by the dt we have to equate it to the 0 because steady state approximation has to be applied upon this intermediate because it is formed in the one step and consumed in the another one. Okay, so here this di by the dt, this will be equal to K1 times the A, and in this minus of the di by the dt, this will be equal to K2 times the I, right? So overall net rate of formation, which is di by the dt, this will be equal to K1 times the A minus of the K2 times the I, and this is equal to the 0, right? So K1 times the A, this is equal to K2 times the I. So from here intermediate I's concentration we get it as K1 by the K2 times the A. So this is gonna be the concentration, so which implies the option D at fourth one, that becomes the correct answer. Okay, next is this question. A reaction between the A and B is carried out for the different initial concentrations and the corresponding half-lives are measured. So T halves are given and A naught and B naught initial concentrations are given. So the rate can be represented as, now we know that T half for the reaction, it is inversely proportional to the initial concentration raised to the power of n minus 1, right? So for the A and B, we have to find the rate, this dependency, that is order with respect to A and B. So for the A, firstly, if I see, this is the ratio variation method, you have to use it. So choose the data for the B in such a way that it's gonna remain to be the constant and A's concentration it is varying. So here if you see in these two datas, that is third and fourth, the concentration of B it is remaining the same, but A's concentration it is varying with the due course of time and the corresponding T halves are given to us. So here the T half 1 to that of T half, that is for at the second initial concentration, it will be equal to A naught 2 upon the A naught 1 raised to the power of n minus 1, right? So T half first one you can consider it as 60 and the second one it is 30. So when the initial concentration it is 60, the initial concentration of A it is 10, and when it is 30 T half, so initial concentration it is 20, this raised to the power of n minus 1, so this becomes 2 and this is also 2, so that means 1 is equal to the n minus of 1. Bases are same, powers can be equated. So from here n value it comes out to be as the 2, which means for the A, with respect to A, the second order reaction is being followed. Okay, now with respect to the B, we have to find it for the B1. So again, for the B, if you have to see it, choose the data in such a way that A's concentration it keeps to be the constant and B's concentration it is varying. So here it is A's concentration is constant and B's concentration it is varying. So this one we can take it. So the T half value it is now 60 and the 60 this is equal to 220 upon the 10 raised to the power of n minus of 1. So this comes out to be as 2 and this is 1. So 1 is equal to 2 raised to the power of n minus 1. This we can write it as 2 raised to the power of 0. So equating the powers, n minus 1 is 0, which implies n value is 1, which means the order with respect to B it is 1 and with respect to A it is 2. That means overall rate expression this is equal to K into the A square and the B. So this is gonna be the final rate expression K into the A2 into the B, which implies the option third it becomes the correct answer. Okay. Next is this. The slope and intercept obtained from the 1 by R against the 1 by concentration of an enzyme catalyzed reaction are this and this. The Michael-Menton's constant, that is Km value, we have to find this out. Okay. So again this is from the Lineweaver-Burke plot. For the enzyme catalyzed reaction, rate is equal to R max into the S upon the Km plus of the S. Now 1 by R, this will be equal to Km upon the R max into the 1 by S plus of the 1 by R max of it. Okay, so from here Km upon the R max, which is the slope, this value is given to us as 300 and the 1 by R max value, this is equal to 2 into 10 to the power of 5 of it. From here just Km value we have to find this out. So Km into the 2 into 10 to the power of 5, this will be equal to 300. So Km it comes out to be as 300 upon 2 into 10 to the power of 5. That becomes 150. 150 into 10 to the power of minus of 5 or 1.5 into 10 to the power of minus of 3 molar. So this is gonna be the Michael-Menton's constant. So this is the answer that is given to us in the option fourth one. So this is the correct answer. Okay. Next is this question. It says the plot of the rate constant versus the root of ionic strength for a reaction which is A plus 2 and B minus follows the linear, refer to the figure. Okay. So this is again from your salt effect. For the salt effect we know that log of K, this is equal to the log of K naught plus of the 2A times the ZA, ZB into the root of ionic strength, right? So if I shift this, it will become log of the K minus of the log of K naught. This is equal to 2A times the ZA, ZB into the root of ionic strength, right? This we can write it as log of the K upon the K naught, which you can take a new rate constant, that is K it is becoming. This is equal to 2. A value it is 0.515 into the ZA ZB. Now here the ionic species it is A plus 2 and the B minus 1, right? So ZA it becomes the plus 2 and ZB it becomes the minus of 1 into the root of ionic strength. So this becomes equal to minus of 2 times the ionic strength, that is equal to the log of the K. So if I see a plot which is for the log K versus the ionic strength, that is Y is equal to the mx. So the slope value that I am getting it is minus of the 2, which means this negative slope I am getting it, right? So which you can see it is in the option 4, it is given to us that log K versus the ionic strength it is coming with the negative slope. That implies the correct answer will be the fourth one. Okay. Next is this question. So this begins your June 2018 paper now. The question it says the elementary step of a reaction A plus B It is giving the 2C with the rate constants, and 2C is giving you the D. If steady state approximation is applicable to C, the rate of production in the reaction is. So you see here it is not mentioned which one is the slow or the fast step of the reaction, and also for the equilibrium it is not mentioned that it is your fast one. So which means the equilibrium approximation we cannot apply it, because for that the essential condition is equilibrium should be there and it should be a fast equilibrium, and this is not mentioned over here, so that can't be applied. So the final rate expression, if you see, it is in the terms of the this one, this second equation that I'm having, it is gonna determine the rate value. So rate is equal to K2 times the C's concentration square it is there. So now C, it is the intermediate. Its value we have to find it out. For that, as I said, equilibrium approximation can't be applied because it is not your fast equilibrium. So steady state approximation has to be applied to determine this C's concentration. Okay, so let us do that. SSA, that means d by dt of the C, we have to equate it to the 0. Okay, so C, it is formed in, it is A plus B, giving us 2C with the rate constant K1, and this is K inverse, and 2C giving us the product D. This is with the rate constant K2. So we can break all of this. It will be A plus B with the rate constant K1 giving us the 2C. So 1 by 2 times dC by the dt. This becomes K1 times the A into the B, right? From the second one, which gives 2C equal to A plus of the B. K inverse is the rate constant, so minus of 1 by 2 dC by the dt. This is equal to K2 times, K inverse times. So this is K inverse times dC square, right? In the second step, it is 2C giving us the D with the rate constant K2. So again minus of 1 by 2 dC by the dt, it will be K2 times the C square, right? So from all of this, the value of dC by the dt we can combine it, that is equal to 2 times the K1 A into the B minus of the 2 times the K inverse of the C square minus of the 2 times the K2 times the C square. This is equal to the 0. From here, the C square value we can find it out. So it implies the C square value, it is gonna be 2K1 times the A into the B upon the 2 times the K inverse plus of the K2. So this is what you will be getting after equated to the 0. So C square concentration, you have got it. So it will be here also 2K2. So substitute this value in the final rate expression, that becomes equal to, it was K2 times the C square. So it's becoming K1 times the K2 into the A into the B upon the K inverse plus of the K2 of it. So we are seeing that the rate it is getting being proportional to A and the B raised to the power of 1 and 1. So this is the answer. So the answer matches, it's proportional to A and B, that is the option A. It will become the correct answer in this. Okay. Next is this question. It says the difference between the activation energies of the reverse and the forward step of the reaction, it is value is given 9.212 RT of it. If the pre-exponential factor of the forward reaction is double to that of the reverse at the same temperature, the equilibrium constant of the reaction it will be. So equilibrium constant, how do we define that? Equilibrium constant is defined as the ratio of the rate constant of the forward to that of the rate constant of the backward direction, right? So this will be, we can write it according to the Arrhenius as A for the forward, which is the pre-exponential for it, into e raised to the power of minus of the activation energy of the forward direction upon the RT upon the this pre-exponential for the backward into e raised to the power of minus of the activation energy of the backward upon the RT of it. Like this we can write it. Now the given condition is that difference between the activation energies of the reverse and the forward steps. So which means activation energy of the backward minus that of the activation energy of the forward. This difference is 9.212 RT, and the other condition it is given that the pre-exponential factor of the forward is double that of the reverse. Activation pre-exponential of the forward is twice the pre-exponential of the backward direction. So these two sub conditions which is given, we can substitute it. It becomes 2 times the AB upon the AB into e raised to the power of activation energy of the backward minus the activation energy of the forward upon the RT of it. This is it is becoming. So this AB and AB term it get cancelled. So 2 times e raised to the power of 9.212 into the RT upon the RT. So this and this will get cancelled out. So 2 into e raised to the power of 9.212. This is gonna be your answer. That is gonna be the K equilibrium. So this exponential power you can find it, and this is gonna give you the answer. Okay. So now next one we are having is this. It says that for an enzyme substrate reaction, the values of the slope and intercept of the plot for the 1 by r versus 1 by s, again from the Lineweaver-Burke plot, this and this values. If E naught value is 10 raised to power minus 6, ratios of the K inverse to the K2 is given. The value of the K1 it will be close to. Okay. So for the enzyme catalyzed reaction, the Lineweaver-Burke plot is 1 by r, it is equal to the Km upon the R max into the 1 by S plus of the 1 by R max of it. Right. So for this one, slope it is equal to Km upon the R max. Its value is given to us as 10 to the power of minus of 2, and 1 by R max it is 10 to the power of 2. So from here R max you can get it as 10 raised to the power of minus of 2. Right, substitute this in the expression Km upon 10 raised to the power of minus of 2. This is equal to 10 raised to the power of, this is not visible I guess. So it becomes Km upon 10 to the power of minus of 2. This is equal to 10 to the power of minus of 2, which means the Km value it is 10 to the power of minus of 4. This is what we are getting. Now we know that Km value, this is defined as the ratio of the rate constants K inverse plus the K2 upon the K1 of it. Right. Now the given condition is that K inverse to that of the K2 value it is 1000. So K inverse, this is 1000 times the K2 value. Right. This you can substitute it. Km value it will be equal to 1000 times the K2 plus of the K2 upon the K1, right? It becomes 1001 times the K2 upon the K1. This is equal to the Km. Now K1 from here it will be 1001 times the K2 upon the Km of it, right? Now this Km value we have calculated it, but we are not knowing is this K2 value. So let us find that. So for that K2 value we need is this R max that we have calculated as 10 raised to the power of minus of 2. This is the one. Now Km R max is equal to K2 times the E naught value. This is equal to 10 raised to the power of minus of 2. So from here K2 it will be 10 raised to the power of minus of 2 upon the E naught value, which is given to us as 10 raised to the power of minus of 6. 10 raised to the power of minus of 6. So that means K2 value it comes out to be as 10 raised to the power of 4 of it, right? So K2 we are getting it as 10 to the power of 4. Now Km we are having, K2 we are having, K1 we can find it out. K1 it was equal to 1001 times the K2 upon the Km. So this will be equal to 1001 times the 10 raised to the power of 4 upon 10 to the power of minus of 4. So this becomes equal to 10 to the power of 8, and this is 10 to the power of 3 approximately. So it becomes 10 to the power of 11 of it. So this is the value of the K1, that is equal to 10 to the power of 11, right? So that means the answer, the correct one, it becomes the option A in this case. Okay. Next is this question. This is from the December 2018. It says for a second order reaction, a straight line is among the following. So for a second order reaction, the integrated rate law expression we have is 1 by A minus of the 1 by A naught. This is equal to the KT. So 1 by A, this is equal to 1 by A naught plus of the KT of it. So Y is equal to the mx plus of the C. So plot of 1 by A versus the time we are having it. So that means the option B, it becomes the correct answer, right? Next is this one. The activation energy of a reaction, it reduces by 12 kilocalories per mole in the presence of the enzyme. Now enzymes are your biological catalyst. So activation energy has been reduced, which means that activation energy in the absence of the catalyst minus the activation energy in the presence of the catalyst, this difference you are having it as 12 kilocalories per mole of it, right? In the presence at 300 kelvins, assuming the pseudo first order kinetics, calculate the factor by which the reaction rate it has increased. So rate constant in the presence to that of the rate constant in the absence, this is gonna only increase. This is equal to, now rate constant values are given, A times e raised to the power of minus of the activation energy in the presence upon the RT, right? And the K in the absence, it will be equal to A times e raised to the power of minus of EA into the EA in the absence upon the RT. A value is the same because reaction we are carrying out is the same only, just the rule of catalyst it is there, and it is gonna affect only the kinetic parameters, right? So this A and A value, it will get cancelled out. It becomes e raised to the power of minus of the activation energy in the presence plus of the activation energy in the absence upon the RT of it, right? So this becomes equal to e raised to the power of activation energy in the absence minus the activation energy in the presence upon the RT of it. That will be equal to e raised to the power of 12 into 10 to the power of 3 calories per mole. R value, it is 2 calories per mole per Kelvin, and the temperature it is 300 Kelvin. So with this Kelvin, this per Kelvin will get cancelled. Calories per mole, this calories per mole, it will get cancelled out. It comes out to be as e raised to the power of 12,000 upon the 600. This gets cancelled out. So it becomes e raised to the power of 20. E raised to the power of 20, that is gonna give you the answer as 5 into 10 to the power of 8 of it. So the option D, it will become your correct answer. Okay. Next is this one. It says the decomposition mechanism of the ozone, it is shown. A condition is then given, then order of the reaction with respect to the ozone. So with respect to the final expression only, the rate will be written. It will be equal to K2 times the O3 into the O. This is gonna be the rate. Now here the O that I am having, it is the intermediate. So SSA has to be applied so that we can eliminate it from the final rate expression. So we have to apply SSA on the O. So for this we need is d by dt of this O equal to the 0. For this, considering the equations, which is O3 is an equilibrium, giving us O2 plus the O, K1 and the K inverse. O3 is giving us the O2 plus the O with the rate constant K1. So d by dt of the O, this is equal to K1 times the O3, right? In the second case, it is O2 plus of the O with the rate constant K1 giving us the O3. So minus of d by dt of the O, this will be equal to K inverse O2 into the O, right? And the final one, which is O3 plus of the O with the rate constant K2 giving us the 2O2. So minus of the d by dt of the O, it is equal to K2 times the O3 into the O, right? So from this one we can combine and get d by dt of the O. This is equal to K1 times the O3 minus of the K inverse of the O2 into the O and minus of the K2 times the O3 into the O. This is equal to the 0, right? So from here the O's value we can find it out. From here this is gonna be equal to K1 times the O3, K1 times the O3 upon the K inverse of the O2, K inverse of the O2 plus of the K2 times the O3, K2 times the O3. So the rate expression, it will become K2 times the O3 into the O's concentration, which was K1 times the O3 upon the K inverse of the O2 plus of the K2 times the O3. So this is what we are getting. Now this condition it was given, that is K2 times the O3, it is much greater than that of K inverse of the O2. K2 times the O3, this is much greater than this. So you can substitute it, that we can eliminate this one because it is very small. So rate it becomes K1 into the K2 into the O3 into the O3 upon the K2 times the O3. So this and this will get cancelled out. Rate becomes K1 times the O3, which means the final rate expression, it is K1 times the O3, which means rate with respect to the O3, it is proportional to its power of 1. That means it is following the first order kinetics, right? So that means it was asked that order with respect to ozone, that is 1. Option B, it becomes the correct answer in this case. Okay. So the next question we are having now is this one. This says K-UNI is the effective first order rate constant for the unimolecular reaction, which is shown to us. The slope and intercept of the plot, which is of the 1 by the K, which is the effective first order, versus 1 by M, are this and this. The value of K inverse to that of K2S. Okay. So the question is from the unimolecular reactions. For the unimolecular reactions, we have the mechanism like this, which is A plus of the A. This is activated with the rate constant K1, giving us the A star plus of the A. Backward direction, it is K inverse. In the second step, A is A star that you have with the rate constant K2. This leads to the product formation. For this, the rate expression that we get, it is K1 into the K2 into the A square upon the K inverse of the A plus of the K2. This is what the rate expression we are getting. Now U and I, they are saying it is the effective first order reaction, which means the A to P is the overall reaction which is taking place. If you write the rate expression for this, it was gonna be K dash times the A. Now K dash that I have written, it is nothing but the KUNI, that is effective first order reaction rate constant only. Okay, so both of this, they are the rate expressions now, so they can be equated. So we can say is K1 K2 into the A square upon the K inverse of the A plus of the K2. This is equal to K dash times the A. So from here K dash value we are getting it as, this is K1 K2 times the A upon the K inverse of the A plus of the K2, right? So now they are saying the plot has been drawn for 1 by the KUNI, which means 1 by the K dash value. So 1 by the K dash, this week will be equal to K inverse of the A upon the K1 into the K2 into the A, right? Plus of the K2 times the upon the K1 K2 times the A, right? So this K2 gets cancelled, this A and A get cancelled. It becomes K inverse of the K1 into the K2 plus of the 1 upon the K1 times the A. This is equal to 1 by the K dash, right? So this is what the plot is for the 1 by K dash versus 1 by M. Now instead of the M, we had taken in the expression that this equation that we have written is the A only, which implies 1 by K dash versus 1 by A plot. It is just there. So this is Y is equal to the mx plus of the C. So for this one, the slope value, we are getting it as 1 by the K1, that is given to us as 4 into 10 to the power of 6 of it. So K1 value, it will be 1 by the 4 into 10 to the power of 6 of it, right? And the other one, K1, 1 by K1 value we are having, we are asked to find the ratio of K inverse by the K2, that is in the intercept value we are having K inverse upon the K1 into the K2. This value of the intercept, its value is 8 into 10 to the power of 11, and K1 value we have calculated it. So 1 by K1 also we were having K inverse by the K2 into the 1 by K1, which is equal to 4 into 10 to the power of 6. It is equal to 8 into 10 to the power of 11 of it. So from here, K inverse by the K2, this comes out to be as this 4 into 10 to the power of 6. It becomes 2 into 10 to the power of 5 of it. So this is gonna be the ratio, and this was a very good question that was from the unimolecular reactions, right? So the answer becomes the option A in this case. Okay. So this was from the unimolecular reactions. So far the plots that is important was the Line-Weaver-Burke plot, but this time in this year, which was 2018 December, this was from the unimolecular reactions. This time it was being asked. Okay. So this was the last question that was to be discussed in this part. So I hope all the solutions are clear to you. So thank you so much for watching. I'll be meeting you in the next video now with the upcoming solutions to the questions. Okay.